welcome everyone at our weekly colloquium. Our speaker today is Professor Mikołaj Korzyński, and he will tell us about probing the space-time geometry using geometric optics.
So, thank you very much for the invitation. So this is a joint work of my whole group, Michele, Julius, and Eleonora. Let me begin with the motivation. So, in my project, I originally wanted to talk about the optical drift effects in GR, and this is the changes of apparent position, redshift, luminosity, and apparent size of distant objects in observer's time, because these are interesting things in cosmological spacetimes. Namely, it turns out that it should be in principle possible to see these variations of distant objects within something like 10 to 20 years, and this would provide additional information about the cosmology where we live in. And these effects are quite subtle because they depend, of course, on the space-time geometry, but also on the momentary positions and motions of the emitter and the observer. So obviously, the drift of the position depends on how both of these move through the space-time, not only on the geometry. And as it turned out, there was no general theory of these observables. So last year I published with an internship student a paper about, basically general paper about these optical drift effects in GR, in geometric optics. And we managed to express in a completely general spacetime all drifts as functionals of the kinematical variables, the 4 velocities and the 4 accelerations of the observer and the emitter in the moment when they're connected by null geodesic, and the curvature tensor along the line of sight, and its first derivative for some of the observables. The main tool was simply the first and the second order geodesic deviation equation along a null geodesic. But slightly later, I realized that actually this is only a small part of a much larger picture. And if you do everything correctly, you can get a very powerful formalism for geometric optics in any curved spacetime. And you can squeeze much more from this type of approach. So what is the problem? The problem is basically light propagation in geometric optics in any spacetime. So we assume that we have an emitter who follows some kind of geodesic, an observer who follows another one. At some moment, the emitter emits electromagnetic or other type of radiation, which follows a null geodesic, arrives at the observer at this given moment. At that moment, the emitter and the observer have their 4 velocities and possibly 4 accelerations. The observer can assign the direction from which he or she sees the radiation coming. That basically you need to project the tangent vector here into the plane orthogonal to the 4 velocity. And now we've got various types of observables. We've got the time of arrival according to the observer's proper time. We've got the position on the sky, which is basically the projection, normalized projection of this tangent vector. Note that it crucially depends on the 4 velocity of the observer because of the aberration effects. You've got the image distortion. So it may happen that this is not just a point source, it has a finite size. And in that case, light from various parts of this object will arrive at a slightly different angle, and we will be able to see an image distortion. On the other hand, we can also think about the parallax, a dual situation where we put another observer slightly displaced with respect to that one and simply compare the apparent positions. They don't have to be the same. Apparent positions of exactly the same event. Finally, we also have the position drift. So we can ask how this position on the sky changes with time as time passes. Here you have to be careful what you actually mean by this notion. Let me just tell you that for geodesic motion, there's a nice geometric candidate, the covariant derivative of this vector r. But for an accelerating observer, you have to be more careful. And the simplest thing to take would be something called the Fermi-Walker derivative of this vector, which is in a way sensitive also to the 4 acceleration of the observer. This is basically, this corresponds to the notion of fixed directions given by some kind of powerful gyroscopes. and you can try to measure the deviation, the rate of change of the position with respect to this type of fixed axis. On top of that, you can also consider the redshift, the change of apparent energy, and its drift. But I won't talk about this in this seminar because I don't have that much time. So let me begin with something I would call the naive approach to this problem. So we've got an emitting body, an observer. We've got a number of moving bodies which generate gravitational fields. We know that they're connected by null geodesic, and a moment later, they're slightly displaced, and they need to be connected by a very different geodesic. Now, you may try to differentiate all these relations and get the observables, but you see, you need to take into account all possible things that are happening here. The gravitational interaction between these bodies, time-dependent light ray bending, time-dependent integrated Sachs-Wolf effect for the redshift, time-dependent Shapiro delays and geometric delays, time-dependent motions of both of these, again affected by these masses, time-dependent aberration effects. Since these guys are changing their velocity, the aberration effects change in time. Time-dependent gravitational redshift, because they are moving in the potential of these two bodies. Time-dependent Doppler effect, and you can think of other things. So it seems like an extremely complicated problem. You cannot really solve in full generality. But that's an illusion. In fact, there is a way to approach it.
This is what I don't understand. If you have a given geometry, G mu is given, then everything is included.
Yes, but not in a simple way. Exactly, I'm talking about it. So assume you've got a metric.
Yes.
This metric defines a set of privileged curves, null geodesics. Then you can specify one word line and another word line. At some moment of observation, you can find a null geodesic which connects these two. Then you can try to find the appropriate connecting geodesics at other times.
No, but for this one geodetic, everything is given.
Yes, but if you're interested in drifts of parallax, you have to vary this geodesic. You have to consider slightly different endpoints.
I'm talking about the geodesic itself. The geodesic is defined by the geometry, and you have just to kind of
Absolutely, but the problem is that it depends. It seems to depend in a horribly complicated way on everything, because the metric depends on everything here in this spacetime.
Once the metric is given, then the calculation.
Once the metric is given, then you can do this calculation, but it's not the smartest way to do it, and you will see why.
There is a simpler way of.
Yes, a different one. So from the nearby null geodesics and fixed observations word lines, you can calculate all these observables. But there is a smarter way, namely, you can realize that you've got the notion of normal coordinates around a point. So if you have a manifold and you take a point, then in its vicinity you can find an appropriate coordinate system where the metric, no matter how curved the spacetime is, the metric is simply flat, plus quadratic corrections due to the curvature right at this point. Well, you can show that these coordinates exist. Now, this is elementary differential geometry. I guess fewer people realize that you can repeat this construction around a geodesic. Namely, if you have a fixed geodesic, then you can find Fermi normal coordinates in which the geometry in the vicinity of this geodesic, all along this gamma, is basically flat, plus tiny corrections when you move away from these geodesics a little bit. And these corrections are again given by the curvature at various points along this geodesic. So you can think about cutting a tiny tube around this geodesic, looking at the geometry and realizing that no matter what kind of spacetime it is, this geometry is flat, plus tiny corrections due to the curvature far away. And how does it help us? Well, in that case, you can think how another geodesic right here behaves if it is contained within this tube. In the leading order expansion, it has to satisfy simply the geodesic deviation equation, in which its momentary position reacts to the curvature along the line of sight. So the whole impact of the curved geometry of the spacetime is only via these tensors along the line of sight. And this approach is actually fairly well known in relativity, much discussed by Singh in his textbook, then by Bażański, and then there is a lot of other works. Let me just mention that an overwhelming majority of these works talks about time-like geodesics, not null geodesics, and null geodesics are quite different here. Okay, so let's go back to the geometric approach. How does this our original problem differ in this language? Well, we've got a coordinate system which works only around this initial null geodesic. This initial null geodesic looks completely flat, like a straight line here. Any displaced geodesic will look like a straight flat line plus perturbations due to the curvature. And now, no matter how complicated the rest of the spacetime is, it can only influence this trajectory via the curvature tensor along the line of sight. So all the dependence on complicated geometry is very much localized to the curvature tensor right here. And you'll see that this matters a lot. So we don't need to know the whole spacetime itself to answer these questions. We just need to know this one null geodesic and the curvature along it. And for some observables, also the first derivative. But I won't talk about them. Okay. So you can show that basically in these corrections you can write down the metric as a Taylor series in y. Y is the free coordinate. So lambda is a coordinate along the geodesic. Y is 3 coordinates parallel to that. And you can show that all these higher terms contain either products or higher derivatives of the curvature tensor. If you introduce something like the curvature radius of the manifold, which is defined as roughly the scale of the curvature, then this is an expansion in the ratio between the size of that and the curvature. Just like in this case, by the way. Okay, so now we see how to set this problem. We just look at the moment of emission and the moment of observation. We know the null geodesic here, and we can just focus on the geometry in this narrow tube around it, namely on the curvature right here, plus the kinematical variables defining the motions. So impact of the spacetime geometry only via the curvature along the line of sight. So now let's state the problem in a different way. So we have a spacetime with any Lorentzian metric. We have 2 distant regions of the spacetime connected by null geodesic. So one of them will be called auditorium, the other one will be the stage. On the stage, various things take place. You've got emission of light, pulsed, continuous, or whatever else from various points. The light travels, it hits the auditorium. In the auditorium, you've got a number of observers who measure time of arrivals, positions on the skies, drifts, and so on. Both of these regions are much smaller than the curvature, so they're effectively flat. And now we have 2 types of effects. The general relativity effects of the light propagation. So the curved geometry between these areas affects the way light travels, but this is captured in the first order geodesic deviation equation. So we just need to know the curvature here. And on top of that, we've got the effects of aberration, time dilation, and so on. But this is just special relativity thing, because each of these regions are is effectively flat. So we just have to apply correctly the machinery of special relativity to understand everything. And the idea is to separate the dependence on the kinematics, the motions of these and these guys, and the dependence of the geometry in all expressions we get. And this is the paper we published recently in Physical Review D. It's a fairly big paper about exactly formulating geometric optics in this program. Okay, so we assume that apart from this fiducial null geodesic or optical axis, as you can also call it this way, you've got another one which starts at a slightly displaced point given by a vector delta x0. We also have, it also can be sent at a slightly different angle. So this is not just L, this is L plus delta L. And notice that this capital delta is corrected for the Christoffel symbols. So we're talking about a covariant difference between this vector and that vector, respecting the spacetime geometry. And now we wonder what happens. So this geodesic for affine parameter lambda naught was here, for lambda e it was here. Now we wonder what happens for a geodesic which at lambda naught was here. How will it behave at lambda e? It will have some kind of deviation with respect to this e, and also some direction deviation. And you can get both of these things simply by solving the geodesic deviation equation with the initial data right here. And the final data gives you the answer here. A very funny thing about the geodesic deviation equations is that it's linear. So you can always formally write the end solution as a linear function of the initial data, which immediately defines 4 bitensors or bilocal things acting from the tangent space here to the tangent space right there. And from the geodesic deviation equation, you can show that in a parallel propagated frame, they can be expressed as solutions of certain matrix ordinary differential equations along the line of sight. So W's are effectively functionals of the curvature here. More precisely, curvature twice contracted with the null tangent vector. This is called the optical tidal tensor. Okay, so this brings us to the issue of bilocal operators or bitensors, which were considered in relativity many times, but surprisingly they're not so much in use apart from very niche applications. And they weren't used all that much in optics. Quite recently only by Uzun, who published her paper a day after we did, and by Fleury, who didn't call them bilocal operators, but in fact they are. It's important to realize that these W's are nonlinear functionals of the curvature tensor right here. Let me just say that in principle you could combine them to a single object, a huge 8x8 matrix. And now it's a funny fact that this matrix is not completely free. It has to be symplectic no matter what the geometry here is. So there is a symplectic form here, which is preserved. And you can also get it by a first order ODE, which you probably recognize. It feels exactly like the ODE for the time evolution operator in quantum mechanics. So without the curvature, you've got a constant matrix here, but you also have a curvature term, which introduces a complicated dependence. So it's basically Schrödinger equations without IH here. Okay, now let's try to relate it to the observables. So we treat this as the reference geodesic, and we ask how the apparent direction has deviated. And here I assume that I only take the linear order corrections in these deviation variables. And you get the relation between the deviated direction according to an observer with given for velocity and the transverse components of this delta L. For getting these quadratic terms here is an approximation, which I'll call the parallel race approximation. I will tell you later why. But on top of that, we need to realize that you cannot join any 2 points here by null geodesic, because simply speaking, light travels with the velocity of c, so not every point here can be joined with any point here. So we have to impose the null condition on this displaced geodesic. I again linearize this condition for getting the quadratic terms. And I get something I call flight light approximation. And it turns out from the geodesic deviation equation that this simply means that the product of delta XO times LO must be equal to the product of delta XE times LE. So there is a compatibility condition between the points at which we're doing the, between the two endpoints. Why do I call it the flat light cones approximation? Well, basically the condition tells us that there is 2 foliations on these 2 regions of the spacetime, the stage and the auditorium. Null foliations given by null vectors, and you can only join them by null geodesics if they lie on the complementary leaves of this foliation. Now, what are the leaves of this foliation? Well, they must be simply the light cones. So if you consider light cones centered at points here, the other region is simply so far away that all these light cones look simply like flat surfaces, flat null surfaces stacked one upon the other, and vice versa. Any null light cone originating here and pointing into the future will look like a flat space here. To say it differently in more astronomers' language, we do not consider transverse Romer delays, only the line of sight Romer delays in the time. Okay, and then we also linearize the dependence on the apparent position and the deviation vector. This simply means that we do not take into account the perspective distortions. So effectively, when looking from here, we treat the light rays in this region as effectively flat. We do not consider their expansion. We consider simply these regions as too small for the expansion or any deviation from parallelness to be visible. So we lose perspective distortion this way. Still, this is not, all these things are not stupid. In fact, you can show that in a flat or almost flat spacetime, this simply corresponds to keeping the leading order expansion in the size of these guys and the distance between them. And in astronomy, this is usually so small that quadratic things can be disregarded. But note one thing: if your spacetime is strongly curved, this is not true anymore. And in fact, both of these effects can at some point start to grow and become significant. So, in principle, you should check order by order whether you can use this approximation. Okay. Another thing to note is that once we use both of these approximations, it turns out that the direction along this null vector L becomes completely irrelevant. Simply, both of the time of arrival and delta R are completely insensitive to adding something proportional to L, either to the position or to the direction. So one component of each of these vectors is just pure gauge. And interestingly, it also holds for the redshift, but I won't talk about that. So in order to get rid of this gauge, instead of considering these vectors to be vectors in the tangent space, we consider them formally in the tangent space divided by L0, in this three-dimensional quotient space. On the other hand, the direction deviation vectors, well, we also divide the space by L0, but we only consider vectors which are orthogonal to L0 itself. So basically, we have a two-dimensional subspace of vectors orthogonal to L0 divided by the null vector L0. This gives the admissible direction deviations here. So we have forgot the gauge component, but interestingly, this trick also helps with the observer invariance of the formalism. Namely, this metric inherits a positive definite metric from the spacetime metric. So you can calculate the products of vectors here without knowing this L component. And this product actually has a very well-defined geometric interpretation. Basically, it gives you the distances and angles given by any observer here on a kind of parallel screen. This is known as the Sachs shadow theorem. Okay. And mappings between these quotient spaces have an observer invariant geometric meaning. Okay. So let's go back to the displacement formulas, the final position in the language of the initial data and the compatibility condition between the emission observation. We formally pass to the quotient space, and these equations are basically equivalent to something like that. This means simply taking the element of the quotient space, and here this means simply the parallel transport. D is something known as the Jacobi operator, which roughly tells you what happens if you deviate the direction of your null geodesic slightly here. It means that the next one will be somehow, and you ask what is the deviation vector at lambda e. This 2x2 matrix tells you what exactly it is. It's a solution of a well-known Jacobi equation. And this is actually a very well-known operator used in general relativity many times. But on top of that, there is also another thing called M. It's an operator which acts from this Q space, so the space of the tangent space divided by L, three-dimensional, into the P space, this two-dimensional space of vectors orthogonal to L. I call it the emitter observer asymmetry operator, and I'll later tell you why. It vanishes in the flat space. Okay. So what do these equations tell you? Well, they give you two language to pass from two possible parameterizations of space geodesic. You can either parameterize them by the two endpoints, a vector here and a vector here, or rather their equivalence classes up to L, but with additional constraint that these products must be equal. Or you can just give the initial data, the initial displacement and the initial direction displacement, which is confined to a two-dimensional subspace. So here the dimensionality is 3 plus 3 minus the time-lapse condition, which is 5. Here the dimensionality is 3 plus 2, which is 5 again. So you can translate between the language of giving to the initial and the final data with the compatibility condition, and the language of giving the initial data exactly from this formula right here. So you parallel transport delta XO right here. You take the difference between delta xe and parallel transport of delta xo. This is a vector which is always orthogonal to L. You take its equivalence class, you subtract m delta xo, and then out of that you can calculate delta LO knowing D. How does it help you? Well, the point is that these operators know everything that can be known about geometric optics in this situation. Let's first think about the linear image distortions. So we've got an object which has an extended size. Under what angle what is the angle taken up by this object? Well, we have to consider a slightly displaced, but only in the orthogonal direction point, delta xe. From this equation we've got here the Jacobi map times delta LO gives us delta XA. So the angle is 1 over, here's a prefactor which gives the aberration effect, d2 minus 1 delta XOE. And this thing is simply called the magnification matrix. It relates the directions, it relates simply the transverse deviations here with the apparent deviation from the on the angle on the observer's sky. So that's the magnification matrix in the gravitational lensing theory. And this gives exactly the magnification and also the, since this matrix does not have to be diagonal, it also gives the image distortion. So if we have a blue ball, this ball does not have to look exactly spherical under these circumstances. It has some size, but can also be elongated, and this is encoded in M. There is also the notion of angular diameter distance, which is simply the ratio between the physical area taken by the cross-section of this object to the angle taken up by this thing. And this is the angular diameter distance. It's, again, expressed in terms of d. Note that both of these things depend via the Jacobi map on the curvature tensor right here, but also on the forward velocity of the observer because of the aberration effect. But there is no dependence on the forward velocity of this emitting body, which might be a bit surprising. But now let's look at the dual situation. We consider the parallax. So we've got a point source, but we displace our observer in a perpendicular direction, and we want to see how the angle has changed. Now, in a flat space, we would not have this term, and we would basically be back to the same equation with a different sign. And this makes sense. In a flat space-time, displacing your observer in one direction is completely equivalent to displacing your emitter in another direction, right? If you move a little bit to the left, this will cause a small change of the position of a body, but it's the same one you would get from by moving your body in the same direction, in the opposite direction on the other end. Now, the point is that in the presence of curvature, this is not true anymore because there appears another term, which is again a function of curvature. Because of that, the relation between the parallax angle and the displacement on the observer's side is slightly different. You can see that there is something new appearing here. This is something I would call the parallax matrix. It relates exactly our displacement with the apparent displacement on the sky. And this is again a matrix. If you imagine looking at a distant object from one point, but also from two other points, and making sure that we're looking exactly at the same light emitted at the same moment, we could in principle plot a triangle on the sky by superimposing these images. And then the relation between these displacement and these angles is given by pi. It turns out that pi is always a symmetric matrix, unlike M. This follows from W being symplectic, but that's a whole different story. You can again define the parallax difference, this time by comparing the size of the triangle formed by these three observers with the apparent size on the sky of this little thing. It's the generalization of the standard parallax measurement of distance. Again, this depends on the forward velocity of the observer, the geometry of the spacetime, but not on the forward velocity of the emitter. Another thing you can get from that very easily is the proper motion or position drift formula. So we want to ask how the apparent position changes when in time when when the second body is emitting continuous light and we're just doing continuous observations. This means we consider displacement along the geodesics, the world lines of these two things. And after a fairly simple calculation, what you get is an exact formula for the position drift rate in any curved space-time, for which you need only the curvature along the line of sight plus the momentary kinematical variables, the forward velocity of the observer, the forward acceleration of the observer, and the forward velocity of the emitter, but not the forward acceleration of the emitter. And this formula by itself has interesting physical consequences. You can see that it's made of a couple of terms. The first one is simply the transverse part of the forward acceleration of the observer, and this is something called the aberration drift. If the body is accelerating, then it's changing its inertial frame, and we know that in different inertial frames, the sky looks a little different. This is called the aberration effect, and a continuous change we call a continuous flow aberration drift, exactly related to the momentary forward acceleration. Then we've got a whole term multiplied by the magnification matrix. So the lensing will also affect the velocity at which we see the objects moving. Then we have something which looks like the difference between the forward velocity of the emitter and the observer, but only the transverse part and with 1 over plus z. And there's this emitter-observer asymmetry operator term. This is automatic orthogonal to L. Now it's instructive to see what this relation looks like in the flat case. Now in the flat case, it's easy, it's a student's exercise to derive in special relativity this formula for the rate of change of the apparent direction from one of light coming from one observer to another. So we've got, again, the same aberration drift. Unsurprisingly, because it's just special relativity effect. Instead of the lensing, we have just 1 over the distance between the observer and the emitter in the observer's frame. And then we've got the same type of difference between 1 over 1 plus z for velocity of the emitting body minus the for velocity of the observer's body, and we take only the transverse part of that. Now, one funny consequence is that think what happens if this body here is moving towards exactly the observer, but with a slight velocity sideways. Now, what happens then is something called the apparent superluminal motions. In this case, the light is strongly blue shifted, so this term is very, very large. And no matter how small the difference of velocities, of transverse velocities is, it can be boosted to enormous rates, which means that small transverse velocity difference may still result in an enormous apparent position drift. And this is known as the apparent superluminal motions, and it's actually observed in real-life astrophysics. And now, a funny consequence of this formula is that you can ask what is the difference between the special relativity and the general relativity. Well, there is no difference, because we have exactly the same term right here, and exactly the same argument applies. If we simply consider an emitter who is moving towards us with a velocity slightly off here, this can grow out of bounds completely. There is no, except that, of course, this is multiplied by a different tensor. But apart from that, qualitatively, this works the same way. Okay, another thing that follows from all this formalism is the relation between the lensing and position drift. If you have strong magnification, so this matrix is very large, then of course all the apparent position drifts will be very large. Not very surprising. And close to acoustic is a situation where you have null geodesics intersecting, and they really happen in space-time. This DAB becomes degenerate, so the magnification matrix diverges, which means that objects are formally infinitely magnified, but also the parallax matrix diverges because it contains d-1, and also the rate of the position drift diverges. So when you see acoustic, this is an enormous amplifier of all drift effects and parallax effects. Okay. I will skip. You can also consider the problem of measuring parallax using the Earth's motion around the sun, but in this formalism, but due to time constraints, I will skip that, I guess. But it's fairly easy to analyze how it works and how you can get this parallax matrix just by looking at the time dependence of the position on the sky, which is known to astronomers, but here there's a relativistic derivation of that. Okay, so So now the situation looks the following. We've got the space-time geometry. We've got the emission and observation point and the null geodesic which connects them. We calculate simply the curvature along this geodesic, and from this curvature we can calculate simply the these 4 operators, or D and M. We also need to supplant the momentary positions and the momentary motions of the observer and the emitter, and out of that we can calculate all the observables. So the dependence of the spacetime geometry is only via this, or more precisely via this. And this simplifies conceptually the problem very much. I will skip the relation to this Higgs formalism because it's not very interesting for this audience. And now in the end I would like to talk about what I consider the most interesting effect of this research, and unexpected one. So again, namely the motions independent observables. So you can look at all the observables you can think of and see how they depend on various types of input data. So one input data is of course the spacetime geometry via the curvature along the line of sight. Another is the kinematical variables on the observer's side, the for velocity and the for acceleration. The kinematical observables at the source's side, it's for velocity and for acceleration. And you can show that Z obviously depends on kinematical observables on both sides. Direction depends on the for velocity of the observer via the aberration effects. And here you've got the dependence for the magnification matrix, parallax matrix, and so on. Now, seeing this, you can ask the question, but is it possible to combine these observables in such a way that you get rid of the dependence of these kinematical variables and you just get the dependence on the spacetime geometry? So is it possible to get rid of all kinematical effects here? And the answer is yes. It's actually fairly easy. One way is to take the minus the magnification matrix times the parallax matrix. Why does it work? Well, look, the parallax matrix has a prefactor due to the aberration effect times the Jacobi map, which only depends on the spacetime geometry. Pi has the same prefactor times the Jacobi map times something like that. So if you multiply these two guys, what you get is simply this thing here, which depends only on the spacetime curvature along the line of sight. So if you combine the magnification matrix to a body with the parallax matrix to a body, you get a result which doesn't depend on how you move through the spacetime or how the body you were using for the measurement was moving through the spacetime. Completely at all orders, there's just no dependence whatsoever. There's only dependence on the spacetime geometry. Okay. Out of that, I want to build a scalar function. So I take 1 minus the determinant of that, which is 1 minus the determinant of the parallax matrix divided by the determinant of the magnification matrix. It's a scalar quantity and it's dimensionless. Just like W doesn't depend on the for velocities here, it only depends on the geometry in this thin tube around the null geodesic. It somehow tells us something about this, gives us some information about this geometry. You will later see what kind of information. Moreover, it's theoretically fairly simple to measure, and this is because you can show that mu is basically 1 minus the angular diameter distance over the parallax distance squared. There is also a plus here, but plus only applies to special situations like counter images. So images which look inverted, or the situations where the parallax is inverted with respect to the standard situation. But this is rare. In most physical situations, just 1 minus the distance by angular diameter over the distance by parallax squared. So, okay, we just look at a single body from 3 different points. We see how exactly, we assume we know its size. We assume it's a standard ruler, this blue ball. We compare its size with the inferred physical size. We get the angular diameter distance. At the same time, we look at the position from displaced points, and from that we infer what the parallax distance is, and we get mu, which tells us something about the curvature and the geometry between these 2 points. Let me also mention that in order to measure the whole M, we would also have to know the parallel transport along this null curve. And this is difficult. In principle, you could try to do it using the polarization of electromagnetic wave, but in astrophysical context, I don't think this is a feasible thing to do. Fortunately for mu, you don't need that. You don't need to really know the parallel transport, or to say differently, you don't need to know the actual position of this body with respect to the parallel transported frame of the observer. It's just, this is irrelevant for this quantity, because this quantity is based only on the areas of body, not on the directions.
So what is the information that you get from this result?
Right here. I'm getting to it. So first of all, note that this is a curvature detector. So if there is no curvature, then there is no m. If there is no m, then this is 1 and mu is 0. So whenever mu is 0, whenever mu is not 0, we know that there is some curvature between these 2 points. Or to say it differently, in a flat space-time, the measurements by angular diameter and by parallax give the same value, namely the physical distance in the observer's frame. And in that case, 1 minus these things is just 0. So this is a bit like the angular deficit formula. Here we take 3 points, we make a geodesic triangle out of that, and from elementary geometry we know that the sum of the angles minus pi is a functional of the curvature within this triangle, namely the integral of this Gaussian curvature. Here we have something similar. We make certain measurements which should give us 0 in a flat space, and the deviation from 0 is a functional, more complicated integrated functional of curvature along one line. Okay, so we have created an observable in which this dependence does not exist, so we can infer directly about the curvature along the line of sight and the space-time geometry. But it's even more interesting when we look at the limit of small curvature. So we assume that the curvature between these 2 points is sufficiently weak that we can just consider it a small perturbation. In that case, mu boils down to this type of integral over the Riemann tensor contracted with L and contracted over the 2 indices. And after a bit of tensor manipulation, you can show that this is simply 8 pi g minus c to 4, the integral of the stress energy tensor multiplied twice by the tangent vector here, times a linear kernel, which is big close to the observer's point and reduces to 0 at the emission point. And that is it. And I guess this answers your question. And this is very fascinating. It's not fascinating, it's less fascinating what is here, it's more fascinating what is not in this formula. So not only we got rid of all the variables concerning the momentary motions of the emitter and the observer, actually, if you have had a relativity course, you know that the Riemann tensor, the curvature, can be split into the Weil part, which basically encodes the tidal forces, the gravitational waves, and everything that is difficult and non-local in relativity. And the Ricci tensor, which is the cosmological constant, and the Ricci tensor, which is directly related to the matter content at a given point. And now it turns out that mu, at least in this limit of 2 sufficiently close points, does not depend on this difficult part, nor on the cosmological constant. It only depends on the matter content along the line of sight. Integrated matter content along the line of sight. And that's very unusual. And this has interesting consequences. Now imagine that you've got this, you do this type of measurement and there is a very heavy body passing nearby. This body will obviously affect the way the null geodesics travel through the space-time. It would simply bend them, change the position, apparent position of the body right here, maybe change even the arrival time. Nevertheless, there is no chance it could ever affect the calculation of mu unless it passes exactly between these 2 points. Why? Because it can only affect the curvature here by the Weil tensor, and the Weil tensor drops out from mu. So only the matter along the line of sight matters. And the same goes for gravitational waves. So you can have strong gravitational waves passing nearby. They will, of course, shake this whole system. This can be detected by careful laser experiments. Nevertheless, it happens that this quantity mu is completely immune to that. Again, because the gravitational waves can only affect the Weil tensor right here. So this quantity has tomography-like properties. Given an observation point and emission point independently of the matter distribution, they tell us something about the matter distribution exactly along the line of sight. It's not exactly tomography because there is this linear kernel here. It's not just the integral of the stress energy tensor, it's something else. Okay, is this thing useful for anything? Well, let me first state that this is basically a very small effect unless you go to cosmological distances. Namely, taking the galactic scale, let's say we measure an object whose distance is 30 kiloparsecs. We measure the parallax, that's possible. We measure the distance by angular diameter. we assume that there is only dark matter here, and assuming the density of dark matter, we got mu equal to 10 to minus 6, which is small. On the other hand, within the galactic disk, this is probably larger by an order or maybe 2 orders of magnitude. But I've seen in one paper so it's not so easy to gauge the matter density within the disk itself. I've seen one paper about that, and I think they claim it's about 10 to 100 larger than this density. And in that case, that could grow to maybe 10 to minus 4. This is still a very small number. On cosmological scales, on the other hand, this becomes significant. You can show that mu is basically 3 to omega m. Omega m is a dimensionless parameter which tells you how much matter you have here, times the redshift squared. So again, this is not a big number for small redshifts. For redshift equal 1, assuming standard cosmological model, we got 0.22. So at z equal 1, this becomes a significant effect. It requires simultaneous measurement of the parallax and the angular diameter distance to an object. So you either need a standard ruler or a standard candle. A standard candle is a body whose absolute luminosity we know, and we compare it with the energy flux. From that, we've got a slightly different distance definition of distance called luminosity distance, but it is known that it's rigidly related to the angular diameter distance. So knowing these things, we could theoretically calculate mu. Because this is a very subtle effect, it will probably require many sources to increase the signal-to-noise ratio. Moreover, at the moment, there doesn't seem to be any kind of annual parallax measurement on cosmological scales. Simply the size of the Earth's orbit, 1 astronomical unit, is too small for that. But it has been theorized for some time that we could, in principle, use the motion of the whole local group with respect to the CMB frame for the measurements of parallax to very, very far away objects. And this was already considered by Kardashev. Then there was an interesting paper by Rasanen and by Puercellini. And recently, a very detailed discussion of this type of measurements by Marcori, who claimed that something like 10 to 30 years should be, in principle, within 10 to 30 years, it should be, in principle, possible to see these effects. Maybe not for single objects, but at least collectively for a collection of quasars. So it's not completely stupid to think about the parallax measurements on these scales. Okay. Still, despite being super difficult, this is a conceptually incredibly simple type of measurement, because you just use standard astrometry of a given object. Moreover, this observable turns out to be completely insensitive to perturbations, external gravitational perturbations. So the fact that your light is also bent by various masses nearby just doesn't really do anything. And you have to consider the peculiar motions on both sides. It has this tomography-like properties of giving the matter density along the line of sight. You may wonder if this is completely new or whether there were ideas like that before. Well, very roughly, yes. So people considered the parallax distance in a homogeneous Friedmann universe, and it was known since 1935 that it carries more information than just the distance by angular diameter or other types of distance. Weinberg, for example, realized that you can measure the curvature of the FRW from the Hubble diagram for the parallax distance. There were papers in the 80s about the parallax distance in FRW plus perturbations, and Rasanen actually even proposed a consistency test for FRW using the parallax distance and luminosity distance. So at the moment we are working exactly on the cosmological applications of this thing with Eleonora Villa. So we have ideas how to use this mu quantity to get zero test of the isotropy of the matter distribution in the universe, or map the local dark matter within the vicinity of this, let's say, our galaxy. On top of that, if you make sufficiently far away the measurements, you can determine one cosmological system, namely omega m, independently of anything else. Also, with Julius currently, I'm looking at the effects of parallax and the drifts in the Schwarzian and possibly Kerr spacetime using this formalism. Yes, just to see how it works and what kind of information about this what kind of information about the Curvature and the Schwarzschild you can get from observations of free-falling objects there. And with Michele Grasso, we are looking at the numerical applications. We know how to do ray tracing, and we also want to see how you get these W matrix in this situation. And we are also working on something I didn't mention, namely on the observables based on the redshift and the reciprocity relation, which follows from the fact that W is a symplectic matrix. Okay, that would be it. Thank you very much.
Okay, are there any questions or comments? Okay, so if not, so I would have a question. So this parameter mu roughly tells you the content of the energy and matter along the
Yes.
line.
Yes, exactly. An integral with a
yes,
kernel.
And at some point you had this diagram where you showed what kind of data is needed for some of those calculations. So can you, so those bilocal geodesics operators, so they depend on R mu, but do they also depend on somehow on the derivatives of this tensor?
No. You'd have to go to the second order. So I assume that you can do away with just the first order geodesic deviation equation. In that case, you've got these W's which depend only on the first one. Of course, you can play with this game further and consider the second order geodesic deviation equation, and then you'll have more operators which will depend on R and
does it actually give you anything more in terms of observational data or corrections are significant and so on, or is it optimal to stop at this level?
In principle, it does tell you something, because in very strong lensing, you've got much more complicated distortions of shapes, which are ruled, which are not just linear distortions, but very complicated patterns. And indeed, in this case, if these objects are large enough, you also have to consider gravitational lensing beyond this type of linear level. So there would be at least potentially applications for that. And there is one paper by Clarkson who considered exactly the second order null GDE in order to understand the appearance of Einstein arcs, namely this type of arc structures in which galaxies look like arc-like structures. This requires higher order corrections.
You said at some point that null geodesics are more complicated. Does that mean that if you would do it for massive geodesics, it would be simpler, and what information can then still be obtained?
So there is a whole, basically a whole huge stack of papers about that in various situations, starting from Sekeres and then later. So what people consider was something called the gravitational compass, where you have a central body, a number of bodies around it, and you simply monitor their distances with respect to time. You assume that the position depend on are given by the first order GDE, and by basically clever algebraic procedures, you can get simply the Riemann tensor, local Riemann tensor, just from observations of the positions or the redshifts of various bodies. So
that's a different approach than studying the path.
Absolutely. And on top of that, there was also a paper quite recently by Flanagan, who considered something called the memory effects of gravitational waves. So you've got a static system, you've got a gravitational bound system. There's a strong gravitational wave passing. It passes, drifts away, and the system does not quite return to its original value. There are differences in the angular momentum and other things. And it turns out that you can understand them also in terms of these bitensorial operators, but along a time like geodesic. But I don't quite understand this paper yet, but the mathematics is basically the same.
Simple question. You mentioned in those estimations of orders of magnitude the coefficient of dark matter.
Yeah.
So where do we know it from, and what is the precision of this estimation? There's this parameter dark matter.
Density?
Yes.
Okay. Let me. So it's the question about the measurements of our galaxy. I'm not very proficient in that. Well, it's first of all the observation of motions of stars in our galaxy, the motions of various satellite clusters, which come into that. The observations of the rotation curve of our disk.
Do you think we know those 3 decimal digits? Is it 009 plus minus? Is it a reliable number? Or
I'd say so. No, I don't think it will change by an order of magnitude. I think the uncertainty was in the next digit here, or maybe even in the second next digit. This is estimated. Okay, they use quite a lot of data, but I think the most important things are motions of galaxy of various clusters of stars and stars within our galaxy.
What about the cosmological scale, dark matter for radiation?
So I take the values taken from the Planck collaboration for these cosmological parameters. And the only one that matters is in fact omega m0. That's it. This is exactly because this quantity is so insensitive to lambda 0 or anything else. It just picks up the omega m term automatically, which is very interesting.
Okay, more questions?
So would it be that at redshift 0.1 it would be an order of magnitude less mu, or is it not that simple?
No, it would be different by 13%. So it's always the parallax distance which is larger. So the parallax distance always gives you a slightly larger value than the angular diameter distance if the if the energy condition holds. And at z equal 1, the difference is 13%, which then means mu equal 0.1.
No, but I'm wondering if you took redshift 0.1.
If you took redshift 0.1,
what would be
that
mu?
would be 32 times 0.31
Okay.
times 1 over 100. So it would be 1%, or less than 1%.
So
0.01.
So that's more feasible because you can hope more for parallaxes at these redshifts rather than.
Actually, these guys here claim something else. It's interesting. They claim that actually it's not the most near parallaxes which are the easiest to get, because it turns out that the effect will be masked by various local effects like the aberration drift and peculiar motions. It is actually z from some kind of 0.1 up to 1, which is in principle easiest to probe.
Okay.
Quite surprisingly.
It's just a short question. We had a question about material particles following these geodesics, and what about this case of neutrinos? Because they have very little mass, so it's almost light-like, but they're still massive. So
they would contribute, of course. They would contribute in exactly the same way, because still they produce. They have a stress energy tensor. You can basically. You just contract it with a null vector in both indices, and you get basically
not in a stress energy tensor, but as instead of light, as the actual signal.
You would have to be able to see the parallax effects from neutrinos.
I know, but I'm just fantasizing.
In principle, it should be possible if you find a way to measure the precisely direction from which a neutrino flows. But I don't think this is likely.
Okay, any more questions? If no, let's thank Mikołaj once again.